Hello, my name is Martin Barus, and I welcome you on the presentation on Bayesian networks from Datalab. So, firstly, we will start with some basic history. Actually, Bayesian networks were created quite recently, 30 years ago, by ČVUT. He actually won an ACM Turing Award in 2011 for his contribution to artificial intelligence and probabilistic and causal reasoning. Interesting fact is that his father was a journalist who was captured and killed by Pakistani militants connected to Al-Qaeda. This is just by the way fact. Bayesian networks are named after famous Thomas Bayes because they use Bayes conditioning, which you will see later. And their informal variant was created in 1913, which is more than 100 years before now. I want to tell you why, or give you some inspiration why Bayesian networks are interesting. Well, the first thing is that they are able to model the whole environment or the whole problem domain if the problem domain has constant number of variables and their relationships do not change over time. And if your domain has these rules or accepts these rules, then you can model your whole environment using Bayesian networks. They're also based on solid mathematical background. They are intuitively interpretable, as you will see, compared to, let's say, neural networks that are quite popular nowadays. When you look at Bayesian networks, you will instinctively know or get what they represent. And they are very universal because you can use Bayesian networks to infer or predict any subset of your variables or any subset of variables of your model based on the evidence that you have. That means based on the values of variables that you can observe. So first, I will explain to you a bit of conditional independence. So let's say you have two variables, x and y, and third variable z, and we say that variable x is conditionally independent of variable y given z if the following is true. And this basically means that the knowledge of y does not give us any new information if we know the state of variable z. You will see how we can use that in y. So this is basically how Bayesian networks look like. They consist of two parts. One part is the graph itself, as you can see. It's a directed acyclic graph. And the other part are our tables for each node. So let's just focus on the graph. Let's imagine that you're a doctor and you're specialized in respiratory tract, meaning you're specialized in things connected to breathing. And you want to model the behavior of your patient and maybe some causes of his disease. So what you can do is that you can create a model that would contain variables that would be all true or false in this case. And in this case, the variables represent whether the patient does smoke. And as you can see, the smoking can cause the patient to have lung disease, and the lung diseases may cause shortness of breath, chest pain, and cough, but the cough can be also caused by the cold. So let's say a patient walks into your office and you see he or she has a cough. Now, you don't know whether he has a cold or he has lung disease, but when you know that the person also has fever, the probability that he has a cold is increased. So this is basically just an insight into how Bayesian networks more or less work. So As you can see, you have one node for each variable of your model, and then you have also the conditional tables. Now, if you focus on the tables, you can see that for each node, you have a table of the node states. Let's take cough, for example. The cough can be, well, the patient either can have cough or cannot have cough. And you have the probability distribution of having cough given its parents. So for each combination of its parents' states, you have probability of this variable. Now, why do we encode, or what do these tables mean, or what do Bayesian networks really do? Well, to understand that, they simply encode the whole probability distribution. I'll write this and put it here. So the joint probability distribution means the probability that each variable has the state it has. And as we know from statistics, we can rewrite the full joint probability distribution as a product of probabilities, or using the chain rule. So the joint probability would be probability of variable 1 times probability of second variable given first variable times probability of third variable given first two variables, and so on, times probability of the last variable given every variable before that. Okay, so this is the formula for joint probability distribution, and we can use that. We can use the knowledge that is, or the fact, which is written here, and that is that each node is conditionally independent of its non-descendant given its parents. It sounds quite hard to understand, but it's really easy. So let's rewrite the whole network. Okay, so I'll write it here. So we have smoking. Can you see it? Okay. Smoking, lung diseases, shortness of breath, chest pain, cough, cold. Now, thanks to the fact that the graph is acyclic, we can order the nodes in such a way that for each node, the node will have higher number than its parents. And how we can do that, or how can we achieve it, right, is that we start by counting from the nodes that have no parents, like this one, and then we continue with order so that each node that we give this number now has already marked parents. Okay, so this specific number 4, 5, 6, 7. And now this is a rule in which we can map the Bayesian network here and the full probability, joint probability distribution into the chain rule. So the joint probability distribution of smoking, lung diseases, cold. I'll start with the order that is here. So we have smoking, cold, lung disease, shortness of breath, chest pain, cough, and fever. And we can rewrite it using this formula in a way we will get probability of smoking times probability of cold given smoking times probability of lung diseases given smoking and cold times probability of shortness of breath given everything that was before it. So called diseases. Now continue here. Probability of chest pain, given everything that was before. So continuing this way. Until we get the last part of it. That's it. Now, knowing that for two random variables that are really independent, conditionally given two variables z, we can apply this formula, which allows us to cross out the variable that are independent. And from this sentence, what it really means is that for each node, if there's another node, like let's say for cold there's smoke, that it is not its descendant, so you can see that smoke is not descendant of cold. And given the parents of cold, well, cold does not have any parents, but if we have, it would have, then given its parents, smoke would be conditionally independent of cold. So if we apply this rule, we can cross out many of the variables right here. So let's say, we will start over here. So cold given smoke, smoking is conditionally independent, so we can cross it out. For Lyme disease, we can cross out cold, but we cannot cross out the smoking because smoking is its parent. And we will continue in this way for each variable. So for shortness of breath, we will leave only the Lyme disease here. For the as well as for the chest pain and for the cough. No, for cough we need to also include the cold because it is its parent. And for fever, the only thing that's left is the cold. So what it leaves us with is the probability of smoke times the probability of cold times probability of Lyme disease given smoke times probability of shortness of breath given Lyme disease times probability of chest pain given Lyme disease times probability of cough given Lyme disease and cold times probability of fever given cold. So as you can see, this formula was transformed into a much simpler one. And the other thing that you can see is that basically for each node that we have, there we have these conditional probability tables right here. So let's say for cough that has two parents, we have the table for each state of Lyme disease and cold, and this is exactly its part in the formula right here. So that would be for the Bayesian network. So for the Bayesian network, we can write that the joint probability distribution can be expressed as a product of each node given parents of nodes. Now from this, you can see that the more parents the node has, the more space the table takes. It grows exponentially, really, because for two states of one parent, you have to have two conditional probability tables. But for two parents, you have to have 2/2 probability conditional probability tables, and it grows exponentially. And yeah, so this is the chain rule, and how Bayesian networks are really just a way to encode the full joint probability distribution in a way that it would be efficient, considering memory. And now that I've shown you this, what do you think a naive Bayes would look like? Naive Bayes is one subclass of Bayesian network. You can express a naive Bayes with Bayesian networks. So let's say we have one output variable, okay, that we want to predict its value, and we have an input variables. So what do you think a Bayesian network would look like for naive Bayes? Do any one of you want to guess? So let's say
Just all that would block.
yeah. So there are edges to the output variable, and which way would the direction go? What do you think? From the output variable into the input variables, or the other way around?
The other way around.
So from the outputs to the input variables, no. So this way?
Yeah, I think.
Yeah, this is what you intuitively think, but it is actually not true, because it would be this way. You'd have one big table here for all the possible states of input variables. But if you do it the other way around, like this, for each node you'd get probability table of x, y states. Let's say true and false, and the output variable states. Let's say true, false. And with using this formula, the joint probability distribution for such a Bayesian network would be the probability of x1 given O times probability of x2 given O times probability of xn given O times probability of O, which is actually the formula for naive Bayes. So as you can see, naive Bayes is just one discrete Bayesian network. Okay, so this is what Bayesian networks look like, but let's take a look about how you can use them. So using Bayesian networks to predict the values that you want to predict is called an inference. Bayesian networks provide you with all the necessary resources that you need for such a task, and they allow you to compute any subset of variables of the model based on any other subset of observed variables. So let's say here if we knew that patient has cough, we could change the probabilities that the patient has also cold and has lung diseases and so on. But the inference itself is generally really hard. It grows exponential in complexity with the number of variables that are unobserved. And even though Bayesian networks allow you to store the full joint probability distribution effectively, in order to compute certain conditional probabilities, it's not that easy. So therefore, there are two approaches. One is exact inference, which can be computationally hard, and when the data set is too big or the computation takes too much time, Monte Carlo methods are used. Now, we'll take a look at one example of how to perform an inference. example that, well, imagine that you have a garden, and when there's rain, well, your garden is good, it's safe, the grass is green and wet and nice. But when you know times are dry, you want your grass to be healthy, so you have a sprinkler. Sprinkler, you know, is the machine that pours the water on your ground automatically. So, and now let's say you came home and you see that, well, okay, my grass is wet, but has it rained or was the sprinkler on? So what are the probabilities? So the question is, did it rain when I know that the grass is wet? Okay, so I want to know the probability of the rain being true, so that means that it has rained, given that I see the evidence that the grass is wet. Now, if I look at the original table and I look at the node rain, I see that I cannot see any conditional probability of rain, given that the grass is wet, so I have to count it somehow. And as Bayesian networks, what they do is they store full joint probability distribution. We have to count the probability from the full joint probability. So we know that this formula actually this equals the probability of rain being true, and at the same time grass being wet, divided by the probability of grass being wet. Okay, so this means probability of one variable and intersection with probability of the second variable. Now to rewrite this using joint probability distribution, we would write it, this is the sum of probability of G being true. The sprinkler, we do not care whether the sprinkler is on and off. Both cases are well, actually good for us. What we care about is that the grass must be wet and it must have rained. And the sum is over S minus the true of S. And this is divided by the sum of probabilities of grass being true, and we do not care really about in what state it is the sprinkler and the rain. So sprinkler and the rain are true, all true and false. And in order to express this kind of space efficiently, I will write that this acronym stands for probability of G equals X, S equals Y, and R equals Z. So using this simplification, we can write this as probability of grass being wet, sprinkler being on, and when it has rained, plus probability of grass being wet, sprinkler being off when it has rained, divided by the probability of grass being wet and all the other possibilities. And each member of this equation is actually one full joint probability distribution. So I'll show you how to count one. Let's say the probability of this, which is the probability of grass being true, sprinkler being on, and the rain has happened. And now we use the formula that is actually equal to the product of each node given its parents. And then it would be, well, rain has no parents, so this is the probability of rain being true, because we care about rain being true, times probability of sprinkler being true while the rain has occurred, times the probability that the grass is wet if the sprinkler was on and it has rained. value we can just simply learn or take from the table. So let's say the probability of rain that it has rained is 0.2. The probability of the sprinkler being on when it has rained is 0.01, and the probability of grass being wet when both the sprinklers was on and it has rained is 0.99. So this would be 0.2 times 0.01 times 0.99. Now, if in this way you can complete all the other remaining part of the equation, and you'll get the probability that it has rained, given that you see that the grass is wet at about 35%. And this is the example of how the inference is done in Bayesian networks. Now, I'll show you some demo. This is a Bayesian network that models the population diversity. It models the gender distribution and the distribution of people's hair length, height, weight, and build. And it models the relationship between these variables. So now let's say we want to predict the person's gender based on another variable. So let's say we saw that the person is 160 centimeters tall. So what do we suppose? Well, we suppose that it's a female with a probability of 92% in the model that this Bayesian network should present. Now let's say that this not really tall, but small or average person has a short hair. Now, as you can see, the probability of this person being male increased much more, but still we would consider this person to be more female than male. Now let's raise the evidence, and let's say that we saw the person, and we only know that he or she has 70 kilos. So, given that the person has 70 kilos, we assume that it is male with 60% probability, but actually it's not that big of a difference considering to the person being female. So now let's add the evidence that we think that the person not only has 70 kilos, but we would consider this person to be large. Now, as you can see, the evidence that we consider person with a weight of 70 kilos to be large made the Bayesian network believe that it is female with 99% probability. So as you can imagine, if you saw a man having 70 kilos, you would probably not assume that he's large. You would not consider him large. Okay, so this was an example of how you can use Bayesian networks. Now there's also a problem how to construct Bayesian networks. So till now I showed you how to use them. But there's a question of how to learn them, or how to create them. So there are two things to consider when we create Bayesian networks. One is the structure, which we will get later, and another thing are the parameters. So let's say you know the structure of Bayesian network, and you want to count the conditional probabilities. So what do? Usually there are two cases. You either get all the data with no missing information, so you have complete data. In this case, you use maximum likelihood algorithm. Maximum likelihood tries to, what's the argument that maximizes probability of the data given hypothesis, which basically means, in our case, if you have only discrete values, that you just count. You take all the possible states of your parents for each node and count the statistics of how much have which value of this node occurred. So it's pretty straightforward. There's not really much to think about. If you do this with continuous variable, you try to you assume that the variable has normal Gaussian distribution, and then the maximum likelihood is a bit more complex. But let's focus about what do we do when we do not have complete data. We use algorithm that's called EM, or expectation maximization. Basically, what you do is that first you just ignore the missing values, and you learn your model without the missing values. And then you use this model that you learn to predict the missing values. And then relearn the model again with the new values in the place where the values were missing. And you then repeat this step a few times until your model has converged, which means that your model has converged when in two continuous steps you predicted the same values for the values that were previously missing. So that's how you estimate parameters. Now let's take a look at the structural learning. So first of all, you need a graph. Okay, so how to get, or the structural learning is about getting the graph part of the Bayesian network. Now, how does that work? Well, obviously, each node of the Bayesian network is a variable of your model. Now, so that's pretty simple. You have, let's say, 4 variables, and the structure has 4 nodes. But how do you create the edges in this graph? So basically, it is a state spacer, which means that you just try to add the edges. You take one edge at a time and you try to add it into each of the points, and you look at the map, which means maximum a posteriori probability of this Bayesian network, and you are trying to find the Bayesian network with the maximum posteriori probability. So why not it means? So this means the maximum posteriori probability means the argument, or means finding a hypothesis that is most likely given the data that you have. So you can write this as this, and because you're trying to find the argument that maximizes this function, and this part of the fraction is equal for each hypothesis, you can just omit it and just write it's the maximum, it's the argument of maximum of the probability of the data given hypothesis times the probability of hypothesis. Now, as you can see, this part is basically maximum likelihood. And there's written that using maximum likelihood is not really good for learning the structure of Bayesian networks, and that is because the structure with the maximum likelihood would be the full connected Bayesian network. So if I have four variables, it would be a model in which each node has all the previous nodes as its parents. Okay, so go like this. And that is in fact just the plain chain rule, so it does not help you at all. So this other Bayesian networks may have the same likelihood, but they cannot get better likelihood than the maximum network. So in order to avoid this is an example of overfitting. We have this part of the equation here, which is called prior. And you can use it as a way to, let's say, punish the Bayesian networks that you do not consider to be likely. So meaning the probability of the hypothesis, so the probability of the Bayesian network will be low. And you can set it in a way that it penalizes the Bayesian network for each edge that this graph has. And also what's important to remember is that you must avoid the cycles, because when you have a cycle, then Bayesian network is really useless, because what it does is that it maps the chain rule into your attributes somehow intelligently, and if there are cycles, it cannot do that. So we also have to check the graph for the cycles when you do structural link. What's also important that when the domain is simple enough, you can create the structure based on, or some experts can come and look at it and say, okay, I know that this structure or the domain structure will be like this. Or you can take the expert opinion for the initial Bayesian network. So let's say the expert says, okay, I know that these two edges should be here because I think they are important, and then you let the algorithm to find the rest, or find the hypothesis or Bayesian network that has the maximum posterior probability. That's how we learn structures. Now there's the question about how can we use time series with Bayesian networks, because up till now every Bayesian network had only variables that did not change in time. So we call the Bayesian networks that handle time series, we call them dynamic Bayesian networks, but they're not really hard. All they do is that they look at each point in the time as one configuration of certain Bayesian networks. So let's say we have variables A, B, and C, and you have Bayesian network in time, one that would look like this, and then you look at the variables in another time slice and do the next one, and it is the same Bayesian network, plus you can add connections between the time slices. So A1 may cause some value change of A2, and also let's say B1 can influence the value of A2. So actually, if you construct a Bayesian network that is able to work with time series, all you do is you create Bayesian networks for as many time points as you want, as far you want your Bayesian network to interact in time, and just model the relationships once again. Okay. Now I'll just show you some real-life application of Bayesian networks. They're used in various fields. They're often used in medical fields or in biomonitoring. They were used on spam filtering. But I want to show you two concrete examples. and that would be the Bonaparte system, which is a system that captures the relationships between family members' DNAs, and this system was used on quite progressively and successfully identified all the victims there, and also helped to solve some unsolved crime. This system was actually created by Netherlands Research Group, which also created another system that is used by Shell. And what Shell uses the system for is to examine the soil and tell if it's important or interesting to use, if it may contain gas or some, whether it has or does not have value for the shell. So these are two concrete implementations or applications of Bayesian network that I found and I liked, and that would be everything from my side. If you have any questions.